In this video, I'm going to cover chapter 3 of my stochastic modeling book. That's the chapter about the convergence of random variables and limit theorems, including the strong law of large number and the central limit theorems, which are two of the most popular theorems in probability theory. More precisely, here are the different topics we are going to cover. As usual, I represented those topics in the form of a directed graph to underline the logical connections among the different topics. And in case you are interested in one particular part of this video, check out the description of the video with the table of content and the specific timing so you can directly jump to the part you are interested in. So like I told you, the two most popular results we are going to see in this video are the strong law of large numbers here and the central limit theorem. So the strong law of large number was first conjectured by Jacob Bernoulli, and the central limit theorem was first conjectured by Abraham de Moivre. And it took a couple of centuries to prove those two theorems. Okay, so that's the goal of the video, that's what we are going to end up with. But first I need to define different notions, so different types of convergence. We need some inequalities and so on. So more precisely, I'm going to start with the different types of convergence when you look at a sequence of random variables. So to motivate like the fact that there are indeed different notions of convergence for random variables. So I assume that you know what it means for a sequence of real numbers to converge to a limit. Now, if instead of a sequence of just real numbers, you look at a sequence of functions, then because a function is an object that is more sophisticated than just a real number, then you have different levels of convergence already for functions. So for instance, convergence pointwise or uniform convergence. And convergence pointwise is weaker than uniform convergence. So if you deal now with random variables, not only you are dealing with functions, but you are dealing with functions that are defined on some probability space. And so that means that in the background you have a probability measure that you can use to measure events or measure the distance between functions or random variables if you look at the corresponding expected value. And so for this reason, because random variables are more sophisticated objects than functions that are themselves more sophisticated objects than just real numbers, you have different levels of convergence. And you can use the measure in the background to have different ways to measure the distance between functions. Okay, so more precisely, we are going to define four main types of convergence for sequences of random variables. Convergence in distribution, convergence in probability, convergence in mean, or more generally convergence in Lebesgue spaces LP, and convergence almost surely. Okay, so that's going to be the first step. We are going to define these different types of convergence. Then the goal after is to understand the relationships between among those different types of convergence, which type implies which other type, and have some kind of hierarchy of that. For that, we'll need to prove first a few results. So we'll need the monotone convergence theorem that I already proved in chapter 1 of my textbook, that was 2 videos ago. We need also a few inequalities. So we will need Markov's inequality and Jensen's inequality to be able to study the relationship among the different types of convergence. Proving those two inequalities, I'm going to also prove Chebyshev's inequality, even if we don't need it at this, we won't need it at this time, we'll need it shortly after to prove the weak law of large number. And so then combining Markov's inequality, Jensen's inequality, and monotone convergence theorem, we'll be able to prove basically that convergence almost surely implies convergence in probability. Convergence in any of the LP space for p larger or equal to 1 implies convergence in probability. And convergence in probability implies convergence in distribution. Okay, so that's going to be the first part of this video. Then we'll go a little bit deeper into those relationships, and instead of proving implications, I'm going to give you counterexamples. And so for that, we'll need the two Borel-Cantelli lemmas, okay, proved by Émile Borel and Francesco Cantelli. There are two lemmas. those two lemmas are about the probability of the lim sup of a sequence of events. So if you have a sequence of events, let's say an, what we call the lim sup of the sequence, it's the new event defined as the event that infinitely many of those events an occurs. Okay, so those two theorems gives us something that I want to call a 0-1 law. Okay, that says that the probability of the lim sup, the probability that infinitely many of those an occur, is either equal to 0 or 1, depending on some assumption that I'm going to give. Okay, then using those two lemmas, we will go back to relationship among the different types of convergence, and what we are going to do is use those lemmas to build counterexamples. So that's going to be examples of sequences of random variables, such that this sequence converges almost surely, but not in mean and not in probability, or converges in mean, but not almost surely and not in probability. Also another example not related to the Borel-Cantelli lemmas of a sequence that converges in distribution but not in probability. So that's going to complete our picture here and shows that all the implications we proved are the only implications that exist. All the reverse implications are in fact not true in general. Okay, so the way we do that is by finding counterexamples, and the two Borel-Cantelli lemmas are the key to finding, to building counterexamples. Okay, so that's going to be all the part about the different types of convergence and the hierarchy among those different types of convergence. And then we'll go to the second main part of the video, that's the part about limit theorems. So the first limit theorem we are going to see is called the weak law of large number. That's a weaker version of the strong law of large number that's in the name. Basically, the weak law of large number gives you a convergence in probability, while the strong law of large number gives you a convergence almost surely. And we will know from this part that convergence almost surely is stronger indeed than convergence in probability. So both theorems are about if you have a sequence of independent, identically distributed random variables, and if you look at the sequence of something that I want to call empirical mean, then this sequence of empirical mean is going to converge to the theoretical mean, or expected value, common expected value of all the random variables, because they are identically distributed. So that's this result that was conjectured by Jacob Bernoulli. So first, we are going to use Chebyshev's inequality to prove the weak law of large number. Okay, this result is very easy to prove. That's just one line. That's pretty easy once you know Chebyshev's inequality. Now, the strong law of large number is much more difficult to prove, and we are going to use a combination of Chebyshev's inequality and the first Borel-Cantelli lemma to be able to deduce the strong law of large number that gives you a convergence almost surely, not just a convergence in probability. I'm going to impose one little assumption in this theorem. That's not going to be a full proof of the actual strong law of large number. We are going to assume that the random variables we are dealing with have finite variance. In fact, the result is still true if the variance is infinite, but we'll need much more theory to be able to prove that. We'll need the concept of martingales and reverse martingale and Kolmogorov 0-1 law that I'm going to cover in chapter 5. So we'll have to wait a little bit to have a complete proof of the stronger result with no assumption on the variance. But at least here I'm going to give you a proof of the strong law of large number with only one little restriction on the variance of the random variables. Okay, so that's going to be like basically the main result of this video. Then after I'm going to give you additional results without proofs because the proofs are way too long. First, I'm going to tell you about the ergodic theorem. So people who worked on ergodic theory are Birkhoff and Farneman. The ergodic theorem is some improvement of the strong law of large number that says that we have the same conclusion the sequence of empirical mean is going to converge to the theoretical mean, even if the random variables are not independent. And instead we need what we call a stationary sequence of random variables. So that's going to be an improvement of the strong law of large number. And then we conclude with additional results. So the main two are the central limit theorem and large deviation estimates. The central limit theorem is going to tell us about fluctuation around the mean, while large deviation estimates are going to tell us about the rate of convergence to the mean. Those two theorems are going to answer questions that are not covered by the strong law of large number. The strong law of large number only gives us some information about the sequence of empirical mean, about the convergence of the sequence, but then we can say a little bit more. And again, the central limit theorem will tell us about fluctuation around the limit, while large deviation estimates will tell us about the rate of convergence. So the central limit theorem can be proved, in fact, using what we call Levy's convergence theorem that was proved by Paul Levy. This theorem basically gives you a characterization of convergence in distribution of a sequence of random variables using the characteristic function of those random variables. I'm not going to give you the proof, but it's just to show you where it comes from. So that's how you can prove the central limit theorem. And I'm also going to tell you about large deviation estimates. So the world specialist in the topic is Varadhan. And again, those large deviation estimates are going to tell us about how fast the sequence of empirical mean is going to converge to the theoretical mean. So first, let's define the different types of convergence for a sequence of random variables. So the context we are going to work in is the following. We fix a probability space, omega fp. I'm taking a sequence x1, x2, xn, and so on, with value in R, but all defined on the same probability space. I'm taking also an additional random variable that I'm calling x, that is going to play the role of the potential limit. X, again, is defined on the same probability space, omega fp. So, first, what do we mean by convergence almost surely? So we say that xn converges almost surely to x if the probability that xn converges to x is equal to 1. So as usual, I'm using this notation as a short to define implicitly a subspace, a subset of omega. And that's exactly the set of little omega in capital Omega, such that xn of omega converges to x of omega as n goes to infinity. That's a pointwise convergence, okay? So I want to point out that because those xn are measurable, they are random variables, so they are measurable, same story for x. It turns out that this set of omega such that xn of omega converges to x of omega is going to be a measurable set, and so in particular an event. And because it's an event, you can indeed look at the measure or the probability measure of this event. Okay, so this is well defined. This set here, again here you have a short for that, is measurable, so you can look at the probability measure of this set. Convergence almost surely just says that xn is going to converge to x pointwise, except maybe for a subset of omegas that has probability measure 0. Okay, so for almost all of them, we are going to have convergence. That's the definition of convergence almost surely. Now, what do we mean by convergence in the space LP or convergence in LP? We use the word convergence in mean in the special case p equals 1. Those spaces are well defined for all p larger or equal to 1. So the space LP of omega fp is exactly the set of random variables such that the absolute value of this random variable at the power p is integrable. So the expected value of the absolute value of x at the power p is finite. Okay? On this set, you can define a norm by taking exactly the power 1 over p of this expected value, of the expected value of the absolute value of x at the power p. That defines a norm on the space LP, and this space becomes a normed vector space. What we mean by xn converges to x in this space LP is exactly convergence for that norm. So that means that the norm of xn minus x, the norm LP of xn minus x, converges to 0 when n goes to infinity. And this thing, again, is defined as the power 1 over p of the expected value of the absolute value of xn minus x at the power p. Okay, again, that's defined for all p larger or equal to 1. That's what we call convergence in LP. Those spaces LP are also called Lebesgue spaces. Then, next definition, what do we mean by convergence in probability? We say that xn converges to x in probability if for all epsilon positive, even small, the probability that the absolute value of xn minus x is larger than epsilon goes to 0. Okay? So exactly the same story as here. This notation is basically a short to define the set of omega in capital Omega, such that the absolute value of xn of omega minus x of omega is larger than epsilon. Again, because xn and x are measurable, you can prove that this set here is a subset of omega that is measurable, so that's an event. And so this defines a sequence of events. Convergence in probability means that the probability of those events goes to 0 when n goes to infinity. All right. So then, last definition, what do we mean by convergence in distribution? That has something to do with the distribution function of those random variables. So I remind you that if you have a random variable x defined on omega fp, the distribution function of x is a function defined on the real line with value in 0, 1. That's defined as capital F of little x equals the probability that your random variable is less or equal to x. Okay? So it's possible that this function is not continuous. It can jump. Okay? You can have point of discontinuity. We say that xn converges to x in distribution if you have a convergence pointwise of the sequence of distribution function of xn to the distribution function of x, not for all x in R, but for all x that is in the continuity set of fx. So that means for all x such that this function, f sub capital X, is continuous at point x. That's what we mean by convergence in distribution. So now, next, the goal is going to be to prove that convergence almost surely implies convergence in probability. We also have that convergence in any of the LP spaces implies convergence in probability. We also have some relationship among those LP spaces. More precisely, if you take P larger than Q, then convergence in LP implies convergence in LQ. We are going to prove all that. Also, convergence in probability implies convergence in distribution. Of course, in view of this diagram, we also have implicitly that convergence almost surely or convergence in any of those LP spaces implies convergence in distribution. So now to be able to prove those implications, we first need a few results. So first we need to use the monotone convergence theorem that I already proved. I gave you a complete proof of that in chapter 1. We also need Markov's inequality and Jensen's inequality. I'm also going to prove Chebyshev's inequality because that's an easy consequence of Markov's inequality, and we will need it soon after to prove the weak law of large number. So first, let's look at Markov's inequality. It says that if you have a non-negative random variable x, then for all epsilon positive, the probability that x is larger than epsilon is less than the expected value of x divided by epsilon. The proof of this inequality is easy. The idea is just to decompose x on the set where x is more than epsilon and on the set where x is less than epsilon, and then use the fact that the expected value is linear. So the proof is just this. You write expected value of x as, or you rewrite, I should say, just x as x times this integer function where x is less than epsilon plus x times this integer function where x is more than epsilon. Then because the expected value is linear, expected value of the sum is the sum of the expected values, and so you end up with that. Because x is non-negative, those two expected values should be positive. Okay, so that means in particular that this one is positive, and so you can get rid of it, but then you have a larger or equal here. So this sum is larger than only the second part. Then in this expected value, because we only look at the set where x is more than epsilon, you can extract the random variable x, put it outside the expected value, but then it has to become a constant. We can just replace it by epsilon, or you can directly replace x by epsilon in this expected value. But then you have an inequality, and then use again linearity to extract this epsilon, so you end up with that. But we know from the definition of integral of an integer function that this expected value is exactly the integral of this integer function dp, which is exactly the measure, the probability measure of x larger than epsilon, so that gives you eventually equals epsilon times the probability that x is larger than epsilon. Now, if you divide this and that by epsilon, you indeed end up with probability that x is larger or equal to epsilon here is less or equal to expected value of x divided by epsilon. And so we are done. That shows Markov's inequality. Now, let's look at Chebyshev's inequality. So Chebyshev's inequality says the following. Now you have a random variable x that does not need to be positive. So it says that for all epsilon positive, the probability of the absolute value of x minus expected value of x larger than epsilon is less than the variance of x divided by epsilon squared. So you basically look at the probability that your random variable is going to deviate from its mean, expected value of x, by more than epsilon. Okay? So I like to think of the variance. So I remind you the variance is defined as the expected value of the square of x minus expected value of x. So the variance is some kind of measure of the randomness of a random variable. If your variance is equal to 0, that means basically that almost everywhere x is equal to its expected value, and so that means that x is almost surely constant, and so in some sense x is not random. At the opposite, if the variance is big, that means that different outcomes of this random variable are going to be all over the place, and so you cannot really control like the distance between your random variable and the expected value of x. So that's kind of the spirit behind this inequality, that says that the probability that your random variable deviates from its mean or from its expected value by more than epsilon can be controlled, but by a term that depends on the variance of x, which is some kind of measure of the randomness of the random variable x. Of course, you also have a factor epsilon here, or epsilon square in this case, because if you take epsilon small, then you are asking for more, and so the bond is not as good. So that's the spirit of Chebyshev's inequality. The proof using Markov's inequality is not difficult. The idea is just to apply Markov's inequality, but to the new random variable x minus expected value of x squared. So x in this context might not be positive, but of course if you take the square of x minus expected value of x, then you end up with indeed a positive random variable, so you can apply Markov's inequality. Okay, so that's kind of the idea. And the proof is just like this. You just said that the probability that we are looking for here is just the same as the probability that x minus expected value of x squared is larger than epsilon squared. You just take the square on both sides. And then if you just apply Markov's inequality, you get that this probability here is going to be less than the expected value of this random variable, so expected value of x minus expected value of x squared, divided by this epsilon here, but now we have an epsilon squared instead, so divided by epsilon squared. And you recognize here expected value of the square of x minus its mean, it's exactly by definition the variance of x. Okay, so you end up with variance of x divided by epsilon squared, exactly what we wanted to prove. Okay, so this inequality, I'm going to use it to prove the weak law of large number. And also that's going to play a role in the proof of the strong law of large number, but only in combination with the first Borel-Conté lemma. Then finally, let's look at Jensen's inequality. So Jensen's inequality says that if f is a convex function, so convex function going from R to R, okay, then f of the expected value of x is less than expected value of f of x. X can be any random variables. So the proof of this inequality is kind of a little bit technical if you look at a general random variable x. Instead, I'm only going to give you the proof when x can only take two values, let's say a and b. That's the proof in this case is based on a very neat geometrical argument. And in fact, even if you look at much more general random variables, the key idea is kind of the same. It's just that there is some extra work to do that is a little bit annoying, kind of technical, not very exciting. I'm only going to focus on like the exciting part, which is this kind of geometrical argument that we can visualize easily when we assume that x can only take two values. So we can just prove everything using a picture. So let's assume that we have like this a convex function. So this curve here is supposed to represent the graph of the function f. Okay, so that's indeed convex. And I'm going to assume that x can only take two values, a and b. So first, let's look at f of the expected value of x. How can we visualize this quantity? Well, if we assume that x is equal to a with probability p, and x equals to b with probability q, and p plus q is equal to 1, then the expected value of x is going to be somewhere in between. That's going to be a convex combination of a and b with weights p and q, okay? And so you can eventually visualize f of the expected value like this, okay? So here we have the length here is like the ratio of those lengths is like p over q, okay? So pa plus qb is somewhere in between. P and q are positive and they add up to 1, so you have a convex combination of the two. That's where you have the expected value, okay? That's how you can visualize it. And of course, f of the expected value is just f of pa plus qb. That's what you read here. Okay, so that's just a visualization of this left-hand side here. So now, how can we visualize this part? So we want to find the expected value of f of x. Because x can only take two values, a and b, that means that f of x can take only two values, f of a and f of b. And that's going to be equal to f of a with the same probability p and f of b with the same probability q, the same two weights as before. Okay? So that means that the expected value of f of x is by definition going to be equal to p times f of a plus q times f of b. Okay? Now, f of a is here, f of b is here. How can we visualize that? Basically, p times f of a plus q times f of b, well, that's going to be exactly here, and I'm going to explain why. So the expected value of f of x is going to be here because the ratio of this length over this length is the same as the ratio of this length over this length. Okay, you have the same p and q for both random variables x and f of x. Okay, and so by, because the ratio are preserved, then we know that this line here is going to be parallel to those two lines here. Okay, so that's the way you can visualize the expected value of f of x. Because of preservation of the ratio, this line should be vertical. Okay, and so we read expected value of f of x here exactly. All right, so now how do we conclude? We see from the picture that indeed the expected value of f of x is above f of the expected value of x. That follows from the fact that the function f is convex. By definition, a function f is convex if each time you take 2 points on the graph of this function and you look at the segment line that connects those 2 points, then the segment line should be above the graph of the function. Okay? Of course, you have some kind of dual inequality. If f at the opposite is concave, then you would switch the inequality, which you can prove using the same reasoning, but then in this case, you use the fact that segment line connecting 2 points of the graph is below the graph, not above, for a concave function. Or you can also use the fact that if f is concave, then minus f is convex. And so that gives you this inequality again, but with minuses, that's going to switch your inequality. So that's how you prove Jensen's inequality when you have a random variable x that can only take 2 values, that just using some basic geometrical arguments. And using this same argument and some technical details, you can extend this result to any possible random variable x. So now let's use the monotone convergence theorem and Markov's inequality and Jensen's inequality to study the relationships among the different types of convergence for sequences of random variables. So the goal, more precisely, is to prove all those implications. We have 1, 2, 3, 4 implications to prove. And let's start with this one. Convergence almost surely implies convergence in probability. All right, so I just remind you the 2 definitions of convergence almost surely and in probability here, because we need to have that in mind to prove the theorem. And the goal is to prove that if xn converges almost surely to x, then xn is going to converge also in probability to x. So in this proof, eventually we are going to use the monotone convergence theorem to conclude. In this proof, we also need to look at the lim sup of a sequence of events. That's the same lim sup that is going to appear when we look at the 2 Borel-Cantelli lemmas. So keep that in mind. So first, let's define a sequence of events. This makes complete sense if you look at the definition of convergence in probability. We are just going to call this event an. I just fix some epsilon positive, and I call an the event that absolute value of xn minus x is larger than epsilon. So the goal is to prove that if xn converges to x almost surely, then p of an goes to 0. So, like I told you, the idea is to look at the lim sup of this sequence. So what do we mean by the lim sup? It's defined here. That's the same lim sup or lim inf that we saw in Fatou's lemma when I covered chapter 1, except that the lim sup or lim inf of a sequence of functions or random variables, like in Fatou's lemma, is obtained by looking at the limit of the supremum of the limit or the limit of the infimum. Here it's the same story, except that what's going to play the role of a supremum for a sequence of sets instead of a sequence of function is going to be the union. All right, so the lim sup is defined like that. That's the intersection over all n of the union for k larger than n of ak. So what you do basically is you look at the tail of the sequence. So you look at all k larger than n, take n large, let's say, you take all k larger than n, and then you look at all those ak, and you look at the union of all the events in the tail. As you increase n, you are going to look at a union over less and less and less events. So this union, as n increases, this union is going to decrease, okay? And so because you have a monotone sequence, a decreasing sequence, it has a limit, and the limit is equal to the intersection, okay? And so that's how you define the lim sup of a sequence of sets, or a sequence of events in this case. That's exactly the limit of the union for k larger than n of the ak, which is the same as the intersection over n of the union for k larger than n of those ak. That's just a definition. That's what we are going to use again when we look at the two Borel-Cantelli lemmas. Then let's turn this event into another event. I'm going to reformulate this intersection of union using the fact that intersection over n means for all n, and union over k larger than n means for some k larger than n, okay? So intersection is like for all, union is like for some. Then, if I use this, I get that this event is the same as the event that for all n, there exists k larger than n, such that ak occurs. But ak, if you remember the definition of ak, that's just the event that xk minus x is larger than epsilon. All right? So that's basically the definition of the lim sup. It says omega is in the lim sup if and only if for all n there exists k larger than n, such that xk of omega minus x of omega is larger than epsilon. Now you see that because epsilon is fixed and positive, if such an omega is in this set, then there is no way that xn is going to converge to x. In this case, the distance between xk of omega and x of omega is going to be infinitely often larger than epsilon. So that means that on this event, xk does not converge, or xn does not converge to x. But because we assume convergence almost surely, that means that the set of omega in this event should be a set with probability 0. Okay? So that's why we have that this has probability 0. This condition contradicts pointwise convergence, which is not impossible, it's just that it happens with probability 0 by definition of convergence almost surely here. Alright, so then next step is just to use the monotone convergence theorem to be able to compute the probability of this event here. And so that gives you just this. You look at the probability here. We take the limit. The goal is to prove that it goes to 0. The limit is equal to 0. This is exactly the event that we call an here. So that's just the limit of p of an. Then I have an inequality here. I'm going to just replace an by this union here. The union for k larger than n of the ak. Indeed, this union is equal to an union an plus 1 union an plus 2 and so on. That's indeed larger than an. Okay, an is a subset of that, so that's why we have this inequality. Now, I'm going to use the fact that I already mentioned that as n increases, this union can only decrease. So that's monotone. This part here is monotone. Okay. And because of that, we can use here the monotone convergence theorem. And so the limit of the probability of the union is just equal to the probability of the limit of the union. Okay? But the limit of the union, because those unions are decreasing, that's the same as the intersection of the union. So that's exactly this event, which is the lim sup. But we just proved that because we have almost sure convergence, this lim sup, this new event called lim sup of an, has probability 0. So we deduce that this is 0, so indeed this probability here that you recognize here has limit 0, so that shows that we have indeed convergence in probability. Okay, so that's the first implication. Then, second implication we want to prove, it's the fact that convergence in LP implies convergence in LQ if P is larger than Q. Okay, again, I remind you here the definition of convergence in LP. I also have the definition of convergence in probability because we are going to right after prove this other implication, so we need to keep that in mind. So we want to prove that if Xn converges to X in the space LP, then it's going to also converge to X in the space LQ if P is larger than Q. I remind you that all of them have to be larger or equal to 1. Those spaces are well defined for PQ larger or equal to 1. All right, so this follows from a direct application of Jensen's inequality. Okay, applied to the convex function f of x equals x at the power p over q. So just a little comment here. P is larger than q, that's the assumption. So p over q, the exponent here, is going to be larger than 1. And so indeed, x at the power something larger than 1, that's a convex function. Okay, so we indeed have convexity because p is larger than q. If you assume that p is less than q, then this function becomes concave. And then all the inequalities we are going to write would be reversed. And so that would be another way to get the result. All right, so then how do we use Jensen's inequality? Well, that's just through this little calculation. We are going to prove, in fact, something a little bit stronger than just this implication. What we want to prove is that, in general, the LQ norm is less than the LP norm if Q is less than P. Okay, that's kind of the proof. So the LQ norm is exactly this, expected value of the absolute value at the power Q, the whole thing at the power 1 over Q. Then I'm rewriting this expression by replacing this expected value inside here by f of this expected value, but I have a power 1 over p here instead of 1 over q. So what I'm just using here is very simple. It's just the fact that f of x, the whole thing at the power 1 over p, it's going to be this at the power 1 over p, so that's x at the power p over q times p, that's x at the power 1 over q, which is indeed equal to this. Okay? That's how you go from here to here. Then, next step, I'm using here Jensen's inequality. Because the function f is convex, I can inject this function inside the expected value, and that becomes expected value of f of the absolute value at the power q. But then, of course, I have an inequality, because the function is convex. Then, next step is exactly the same kind of transformation as to go from here to here. To go from here to here, now I'm using the fact that f of x at the power q, okay, is, well, x at the power q at the power p over q. That's exactly x at the power p, okay? And so I can replace this absolute value at the power q here, f of this absolute value, by just the absolute value at the power p. But then here you recognize the LP norm, okay? So that's the LP norm here. And then by assumption, we said that Xn converges to X in LP. That means that this norm here converges to 0 as n goes to infinity. And so by the inequality, that's also true for the LQ norm. And so we have that Xn converges to X in the space LQ for Q less than P. All right, so that shows this implication. So now let's show the next one here. Convergence in any of the LP spaces for any p larger or equal to 1 implies convergence in probability. So again, you have the two definitions here we need to have in mind. If Xn converges to X in the space LP, then Xn converges to X in probability. So that's a direct application of Markov's inequality. The proof is very short. This one is easy. you just use the fact. So first we want to prove this, so we are going to fix some epsilon positive and look at the probability that absolute value of xn minus x is more than epsilon, okay? That's what we need to look at, and we want to prove that this goes to 0. By Markov inequality, you remember that this is because this random variable, of course, absolute value of xn minus x is a positive measure, positive random variable. We can apply Markov's inequality, and this probability is less than the expected value of xn minus x in absolute value divided by epsilon. So that's exactly what we have here. And that's this expected value here is exactly the L1 norm of xn minus x. If you go back here, that's indeed, if you take q equals 1 here, for instance, you get indeed expected value of the absolute value of xn minus x, and that's it, okay? So this is the L1 norm, but we just proved that convergence in LP implies convergence in LQ if P is larger than Q. So if you take in this theorem Q equals 1, you would get that the L1 norm here is less than the LP norm, okay, for all P larger or equal to 1, and that's what I'm using here. We have here, this expected value is just the L1 norm, and I'm just using that this L1 norm is less than the LP norm, again divided by epsilon, but by assumption xn converges to x in the LP space, so this goes to 0, which proves with those inequalities that this indeed goes to 0. That's exactly the definition of convergence in probability. All right, so that shows that xn converges to x in probability. Then, last implication, convergence in probability implies convergence in distribution. Again, you have the two definitions we need to have in mind here. Convergence in distribution, I remind you, means that the distribution function of xn at point x is going to converge to the distribution function of x at the same point x for all x at which f sub capital X is continuous. All right, so this proof is a little bit more technical. We don't use any fancy tool, but it's a little bit more technical. So first, I'm going to take two random variables, y and z, and some positive real number epsilon. And I'm going to use the fact that the event that y is less than z is a subset of the union of the events z less than z plus epsilon, so z is like any real number, union the absolute value, the event that the absolute value of y minus z is more than epsilon. So this thing is easy to see. You just say that assume that y is less than z, then either z is less than z plus epsilon, or if it's not the case, then z is going to be strictly larger than z plus epsilon. But in this case, because y is less than z and z is more than z plus epsilon, then the distance between y and z should be more than epsilon, which gives you this event. Okay? So eventually, if this event occurs, then at least one of those two events must occur. Either z is not that big, or if it's too big, then the distance between those two ones should be more than epsilon. All right, so that's the first step. Then, now I'm going to take probabilities on both sides. Okay, if I look at the probability of this event, I get exactly, so probability that y is less than z, that's less or equal to z, that's exactly by definition the value of the distribution function of y at point z. I can do the same here. I'm also going to use the fact that because of this inclusion, the probability of this event is less than the probability of this event, and also the fact that the probability of a union is less than the sum of the probabilities. Okay? So if we do this, we get exactly that probability that y is less or equal to z, which is f sub y of z, is less than the probability of this event, which is exactly the value of the distribution function of z at point z plus epsilon, plus the probability of this event. And here I don't change anything, all right? So now, the next step is to use this inequality in two different contexts, taking specific values for y, z, and little z here also. I'm going to take y and z equals to either xn or x, the limit, and z can be equal to little x, like here, or x plus epsilon, x minus epsilon. So more precisely, if we take, we take two different cases, so let's just look at the first one because they are both like identical. So if I take y equals xn, z equals x, little z equals little x, then this inequality becomes f sub xn of x less than f sub x of x plus epsilon plus this probability here, the probability of this event, but now with xn minus x. And we know that this goes to 0 by the assumption that xn goes to x in probability. Okay? Then, same story, if instead you take y equals x, z equals xn, and little z equals little x minus epsilon, then you would get this, this second inequality here, if you replace those three values by those three ones in this inequality there. Alright, so now, you see that by the assumption of convergence in probability, those two probabilities here, these are the same, they are both going to converge to 0. So more or less, we have that fxn of x is sandwiched between fx of little x minus epsilon and fx of little x plus epsilon. Now, if this distribution function is continuous at point x, then if I take the limit of that and the limit of that when epsilon goes to 0, I converge to exactly this limit here. That's how we get the result, okay? So, more precisely, to conclude, we just said that if we take a point x at which f sub capital X is continuous, then we can rewrite this potential limit here. You recognize that's the same term. This is exactly the limit when epsilon goes to 0 of f sub x of little x minus epsilon. Okay? Then, now I'm going to use this inequality. I know that this quantity here that you recognize here is less than that, but plus this probability, but this probability goes to 0 when n goes to infinity. So I'm taking the limit. Here I could take limit when epsilon goes to 0 and n goes to infinity at the same time, but this does not depend on n, so I don't take the limit when n goes to infinity, and this does not depend on epsilon, so I'm not taking the limit when epsilon goes to 0, but strictly speaking, you can take the two limits everywhere. But okay, so then if you take the limit when n goes to infinity in this expression, this disappears, that goes to 0, because we have convergence in probability, and we end up with only that term, okay? So that's where this comes from. And then, after using this inequality, now I can use this over 1 and say that this f sub xn of little x is also less than f sub x of x plus epsilon, with again the limit when epsilon goes to 0. And again, because we assume that the function fx is continuous at point little x, this limit here is just f sub capital X of little x. And we are done because you recognize that here, the quantity here is the same as here, which means that those two inequalities in fact are equations. And so eventually you end up with that the limit when n goes to infinity of f sub xn of little x is equal to f sub capital X of little x, which is exactly this. So that's true for any x at which this function, this distribution function is continuous. And so that shows indeed that convergence in probability implies convergence in distribution to the same limit. So now let's prove the two Borel-Cantelli lemmas, and I remind you that we are going to use both lemmas to explore further the relationship among the different types of convergence and construct some counterexamples. We are also going to use again the first lemma to prove the strong law of large number. Okay, so here are the two Borel-Cantelli lemmas. They are kind of converse of each other, but in the second one you need a condition of independence. So in both of them, you consider a sequence AN of events in the sigma algebra F. The first lemma tells you that if the infinite sum of the probability of AN is finite, then the probability of the lim sup of the AN is equal to 0. So we just define the lim sup of a sequence of events. That's the event that AN occurs for infinitely many n. So the first lemma basically tells you that if the infinite sum of the probabilities is finite, then with probability 0, infinitely many of those events are going to occur. Okay, so you have only a finite number of them that are going to occur. You have a converse, but you also need to impose independence. Now, if the infinite sum is equal to infinity, and you have independence among those events AN, then now the probability of the lim sup is equal to 1. That means that with probability 1, infinitely many of those events are going to occur. All right, so that's a kind of something that we call a 0-1 law in probability theory, which says that this event occurs all the time or occurs never, more or less. Okay, so it's easy also to see that the condition of independence here is important. If you drop this condition, it's easy to find a counterexample of sequence AN such that the infinite sum of the probability is infinite and still this probability of the lim sup is not equal to 1. So for instance, just take a sequence of events AN such that with probability 1/2 all the events occur, or with probability 1/2 none of them occurs. Then in this case, that's easy to see that basically the occurrence of the first event, okay, occurs with probability 1/2 or does not occur with probability 1/2 is going to define the rest of the sequence, whether the other events occur or not. So it's easy to see that for all n, P of AN is equal to 1/2. So the infinite sum here is indeed equal to infinity, okay? But obviously you don't have independence. If one occurs, then they all occur. So that's this sequence is not independent. And then clearly in this case, with probability 1/2, all of them are going to occur, or with probability 1/2, none of them is going to occur. So that means that the probability of the lim sup is equal to 1/2, not 1. So that shows a counterexample in this second case. All right, so now, how do we prove the first lemma? So, first, I remind you again the definition of the lim sup. We just did that to prove that convergence almost surely implies convergence in probability. The lim sup of the AN is the intersection over all n of the union for k larger than n of the AK. That's exactly the event that for all n, there exists k larger than n such that AK occurs. That means exactly that AK occurs for infinitely many values of k, so that this event is just the event that infinitely many of those AN occurs. All right, so that's the definition. To prove the first lemma, the idea is to introduce a random variable n that's going to keep track of the number of times those AN are going to occur. So more precisely, I'm just introducing this random variable, n is the infinite sum of the indicator function on AN. Okay? So if we look at the value of n of omega for a particular omega, you see that this indicator function at point omega is equal to 1 if and only if omega belongs to n, okay? So this n of omega basically is going to count the number of sets, the number of n, such that omega is in AN, that's an infinite sum of zeros and ones, basically, that count the number of occurrences of those event AN. So what this means is that if n is equal to infinity, then that means that infinitely many of those AN occur. But if n of omega is finite, that means that for this particular omega, only a finite number of those AN are going to occur. So to prove the first lemma, the idea is just to say that if this infinite sum of probabilities is finite, then this random variable n is going to be almost surely finite. The random variable that counts the number of occurrences should be almost surely finite. And so to prove that, it's enough to just look at the expected value of n and prove that it's finite. Okay? If a random variable has a finite expected value, then it must be almost surely finite. And for that, we are going to once again use the monotone convergence theorem. So the proof is just here. The expected value of n is equal to the expected value of this infinite sum. I'm just rewriting the definition of n. And then, using the monotone convergence theorem, you can extract the infinite sum outside. We already did that several times in previous videos. The idea is just to think of the infinite sum as the limit of the partial sums. Then, the sequence of the partial sum, because those indicator functions cannot be negative, the sequence of the partial sum is monotone increasing. Okay? That's why you can use the monotone convergence theorem. Hidden behind, we also use the fact that the expected value is linear to also extract the partial sum. Eventually, by linearity of the expected value and by monotonicity of the sequence of partial sum, and so we can use the monotone convergence theorem, you can eventually put this infinite sum outside the expected value. All right? So you end up with expected value of n equals infinite sum of the expected value of indicator function on AN. But the expected value of the indicator function is just the probability of this event. Okay? So you end up with expected value of n equals this infinite sum that we recognize here. But by assumption, it's finite. So that means that expected value of n is finite. If the expected value of n is finite, then n can only be almost surely finite. Okay? Which shows the first lemma. Okay? This implies that the lim sup of those AN, which is exactly the event that AN occurs infinitely often, and so the event that this random variable n that counts the number of occurrences is infinite, this probability is equal to 0, and so we indeed have the first conclusion. All right, so that's the first lemma. Now, to prove the second lemma, we use independence to argue that the probability of this intersection of complements is equal to this product. So, the idea here is simple, saying that those events, and I have a finite number of them here, saying that those events are independent implies if those events are independent, then their complements also are independent. Okay? You can easily prove that if A and B are independent, then A and B complement are independent, A complement and B are independent, and A complement and B complement are independent. You can extend that for any finite family of events. That's what we are using here. By independence, those complements here of those events are independent, and so the probability of the intersection is just equal to the product of the probabilities. So this probability is the product of P of AN complement times P of AN plus 1 complement and so on. And I just rewrite P of AN complement as 1 minus P of AN. That's it. Okay? And you do that for all those events. So you end up with this product. Then after we just use a basic inequality in calculus. 1 minus x is less than e to the minus x. You apply that for each term, you end up with this probability is less than the product of those exponential. Now, the good thing when you have those exponential is that a product of exponential is just the exponential of the sum. And so now you can replace this expression just by exponential of minus the sum of p of n plus p of n plus 1 and so on up to p of n plus m. Okay, m is fixed here, but we are going to take the limit after when, yeah, we take the limit here when m goes to infinity. So, if you look at this part here, that's exactly a piece of the sum there, okay? Because we assume that this infinite sum is infinite, that means that all the remainder, okay, even if you start the sum late, not at n equals 0, but for n large, still the remainder is going to be infinite, okay? That's what we use here to say that in the limit when m goes to infinity, by this assumption, this sum here is going to go to infinity, but exponential of minus infinity is 0, okay? And so we get that this goes to 0 as m goes to infinity, okay? Now, to conclude, we again use the monotone convergence theorem, okay? We look at the probability of the lim sup here. We want to prove that it's equal to 1. Then in this case, we use the monotone convergence theorem here to say that the lim sup is equal to exactly this intersection of union, which is the same as the limit of the union, but the sequence of the union here is decreasing or non-increasing. And so we can rewrite the limit, like probability of the limit of the union as the limit of the probability of the union. We can extract the limit using the monotone convergence theorem because the sequence of the union here is monotone, okay? That's what we do here to go from this line from this expression to this expression. And then here, you recognize exactly, so the union that is here, okay, that's the union of the tail, but we just prove that the complement of that, which is the intersection of the complement here, goes to 0. So that means that this, without this part, when m goes to infinity, that should go to 1, okay, like 1 minus the probability of the complement. And so indeed we get that the probability of the lim sup is equal to 1, which shows the second Borel-Cantelli lemma. So now let's use the two Borel-Cantelli lemmas to explore even more the relationship among the different types of convergence and build some counterexamples. So more precisely, I remind you the picture of the implication we proved here. The goal is to prove that there are no other implications. That's the best we can do. So more precisely, we are going to prove that there exist sequences of random variables that converge to a limit x almost surely, but not in L1 or in mean. At the opposite, there are also sequences of random variables that converge to x in mean, but not almost surely. That's going to show that those two types of convergence are not related. None of them implies the other one. Because each of them implies convergence in probability, those two counterexamples are going also to show that convergence in probability does not imply convergence almost surely, and convergence in probability does not either imply convergence in mean. Okay? One last counterexample we'll need is an example of a sequence of random variables that converges to a limit in distribution, but not in probability. This counterexample is easy to design. We don't need the Borel-Cantelli lemmas to do that. So, step one, the goal is to prove this theorem. That's again not proving implication, but proving that some implications are not true. So the goal is to design counterexamples. That's it. So we want to prove that convergence almost surely does not imply convergence in mean, and convergence in mean does not imply convergence almost surely. So for that, I'm going to consider this sequence of random variable. I'm taking a sequence xn of random variable that I assume to be independent. And each of those xn is going to be equal to 0 with probability 1 minus pn, and to little xn with probability pn. right now, Pn and Xn are just parameters that can be whatever, and we are going to fix them after to build our counterexamples. Right? So I'm using also this assumption that those random variables are independent to be able to use also the second Borel-Cantelli lemma. In this theorem, you need independence among events, and we will need that those events that xn equals 0 for different values of n are indeed independent to be able to use the second Borel-Cantelli lemma. That's why I also assume that xn is independent. Those xn's are independent. So, let's look at this example. Eventually, we are going to take Pn going to 0 and Xn going to infinity. Okay, so that gives you random variables that are more and more and more and more likely to be equal to 0, but with a small probability as n increases, those random variables can be arbitrarily large, but with only a small probability. So, taking Pn going to 0, a natural candidate for the limit of xn would be the random variable equal to 0 everywhere. Okay? And that's going to also simplify the calculation if we assume that. So let's look at whether xn converges to 0 or not. Okay? And depending on the choice of Pn and xn, we can force the convergence to 0 almost surely but not in L1, or in L1 but not almost surely. So first let's look at the condition for convergence in L1 to 0. So for that, we just look at the L1 norm of xn minus the limit, because the limit we have in mind is 0. The L1 norm is just the expected value of absolute value of xn, but those xn are positive, so that's just the expected value of xn without the expected value. In this case, it's easy to see that the expected value of xn for all n is going to be 1 minus Pn times 0 plus Pn times xn. So that's how we get that expected value of xn, which is the same as the L1 norm of xn minus the limit 0, is equal to xn Pn. From this, we deduce that xn indeed converges to 0 in mean, in L1, if and only if the product xn Pn goes to 0. Alright, so now let's look at the condition for convergence of xn to 0, but almost surely this time. So in this case, we use the two Borel-Cantelli lemmas. I'm just going to see that the probability that xn is different from 0 from this expression that just equal to Pn. Okay? And so clearly xn is going to converge to 0 if and only if this event that xn is different from 0 occurs only a finite number of times. Okay? And so we look basically at the lim sup of the sequence of this sequence of events. And so by the two Borel-Cantelli lemmas that we can both apply because of independence, so those events are indeed independent for different values of n. So by the two Borel-Cantelli lemmas, we can see that xn converges to 0 if and only if those events occur only a finite number of times. That means that the probability of the lim sup should be equal to 0. And we saw that this happens if and only if the infinite sum of those probabilities is finite. So that's the infinite sum of the Pn is finite. So now we have basically a characterization of convergence to 0 in mean and convergence to 0 almost surely based on the value of xn and Pn. Alright, so now let's choose basically xn and Pn in such a way, like the last step is just to choose xn and Pn in such a way that this is not true but this is true, or this is true but this is not true. And we have our counterexamples. So that's pretty easy to do. So let's take Pn going to 0, but in such a way that the infinite sum is infinite. Well, example, Pn equals 1 over n. In this case, Pn does not go to 0 fast enough, the infinite sum is equal to infinity, and the convergence almost surely does not happen. Okay? So let's take Pn equals 1 over n, but then we need to take Xn in such a way that Xn times this Pn indeed goes to 0. For example, Xn equals square root of n. If Xn equals square root of n, then square root of n divided by n is 1 over square root of n, that goes to 0. So we have convergence in L1, but not almost surely. So that's our first counterexample. If you take Pn equals 1 over n and Xn equals square root of n, in this case, this is not satisfied, so you do not have convergence almost surely, but this is satisfied, so you have convergence in L1. Now, because the fact that Xn converges to 0 in L1 also implies that Xn converges to 0 in probability, that shows also that you may have sequences of random variables that converge to a limit in probability, but not almost surely. So you have basically two counterexamples. This does not imply that, and this does not imply that. All right. So now, second counterexample, we want to take Pn small enough, decreasing to 0 fast enough so that the infinite sum is finite. Example, let's take Pn equals 1 over n squared. In this case, indeed, the infinite sum is equal to pi squared over 6. It doesn't really matter what's the limit, but you just have to know that the infinite sum of 1 over n squared is finite. And so we are going to have convergence almost surely to 0. But we want to find Xn in such a way that this does not go to 0. Example, let's take Xn equals n cubed, for instance. And so Xn times Pn becomes n cubed over n squared, that's equal to n, that goes to infinity. Okay, so if we take this, Pn equals 1 over n squared, but Xn equals n cubed, then in this case, this condition is satisfied, so we have convergence almost surely to 0, but this condition is not satisfied, so we do not have convergence in mean or in L1. As previously, you can say that because convergence almost surely to 0 implies convergence in probability to 0, this also gives you an example of sequence of random variable that converges in probability but not in L1. Okay, so that's our counterexamples, showing that this does not imply that, this does not imply that, and this one does not imply any of the two. Now, last counterexample, we want to find a sequence of random variables that converges in distribution but not in probability. This one is pretty easy because if you look carefully at the definition of convergence almost surely in LP or L1 and in probability, they are about the random variables themselves, while convergence in distribution doesn't look really at the random variables themselves, their outcome, but they only look at the distribution function. So the counterexample in this case is pretty easy. You can just take the Xn to be independent Bernoulli random variable with parameter 1/2. Okay, so that means that all those Xn independently are equal to 0 with probability 1/2 or 1 with probability 1/2. Okay, and so clearly all those Xn, because they have the same probability mass function, they also have the same distribution function. And so the sequence of distribution function is constant. And so clearly, Xn is going to converge to the random variable X that has, whose probability mass function is Bernoulli with probability 1/2. So in this case, because the sequence of distribution function is always the same, like all the distribution functions are the same, we obviously have convergence in distribution, okay? But we do not have convergence in probability, because if you take Xn and X to be independent Bernoulli random variable with parameter 1/2, then the probability that the absolute value of Xn minus X equals 1, let's say, is exactly the probability that one of them is 0, the other one is 1. And that gives you two possibilities, 0, 1, 1, 0. You have a total of 4 different outcomes for the two random variables together. Each of the two outcomes, therefore, has probability 1/4. And so that tells you that the probability that absolute value of xn minus x is equal to 1 is going to be equal always to 1/2. That does not go to 0, and so that shows that even if the sequence here xn is constant in distribution, and so you have convergence in distribution, still you do not have convergence in probability. So convergence in distribution does not imply convergence in probability. So now let's move to the second part of this video, focusing now on limit theorems, starting with the law of large number. So more precisely, we are going to first prove what we call the weak law of large number that gives you a convergence in probability using Chebyshev's inequality. And then after, we are going to combine Chebyshev's inequality and the first Borel-Cantelli lemma to prove a stronger type of convergence almost surely, and that's going to give us what we call the strong law of large number. All right, so here are the two theorems, law of large numbers, the weak version, the strong version. So in both cases, we assume that we have a sequence of random variable xn that are independent and identically distributed. Because they are identically distributed, in particular, they have the same mean, and we are going to call the common mean of all those xn, the common expected value, we are going to call it mu, and we assume that mu here is finite, okay? So, in both cases, we are looking at this quantity that I want to call the empirical mean. So, we are basically looking at the sum of the first n of those random variables, x1 plus x2 plus x3 and so on up to xn. That's the quantity that I'm calling Sn. That's a new random variable, okay, that consists of the sum of the first n. And I divide this by n, and so eventually I'm looking at some kind of empirical mean of this quantity. All right? So this is the empirical mean of the first n of those random variables. And the weak law of large number says that this new random variable is going to converge in probability to mu, the theoretical mean. And the strong law of large number says the same thing, but something stronger. That's why we call it the strong law of large number. It says that, in fact, the convergence is not just in probability, it's also almost surely, which we proved is a stronger type of convergence. So, there is something interesting in the statement of those theorems, regardless of whether you look at the weak or strong law of large number. This says basically that the empirical mean converges to the theoretical mean. And the empirical mean is basically what you would observe, okay? Even if you don't know anything about probability theory, you can see something that happens at random that corresponds to different outcomes of the same random variables. And what the weak and strong law of large number tell you is the fact that if you see enough outcomes of the same random variable, as long as those outcomes are independent, then the mean that you see, the empirical mean, the mean that you observe, is going to indeed approach the actual expected value. Okay? Now, you can also apply the weak law or strong law of large number looking at particular type of random variables that are of the form of indicator function on an event. So of course, again, you assume that things are independent and identically distributed, in which case what you would do is basically repeat an experiment n times for n large and look at, when you look at this quantity, it's going to be 1 over n times a sum of zeros or ones, 1 each time some given event happens, 0 when this event does not happen, and this becomes the fraction of time some event happens. In this case, particular case where xn is an indicator function, in this case, what the law of large numbers tell you is the fact that the fraction of time you see something happening, if you repeat an experiment enough time and you look at the fraction of time a given event is going to happen, this quantity is indeed a good approximation of the limit mu here, but mu in this case, that would be expected value of an indicator function, that would be the probability of the event. So, conclusion, in both cases, what those theorems tell you is that if you observe enough outcomes of the same random variable, as long as things are independent, and you look eventually from that at the empirical mean, what you can observe, this is indeed a good approximation of the theoretical mean. If you take the particular cases where xn is an indicator function, and you repeat an experiment often enough, and you look at the fraction of time a given event is going to occur, then in this case, the fraction of time you see the event happening is indeed a good approximation of the probability. Okay, so in some sense, those theorems, they connect our intuition of what should be an expected value or what should be a probability as kind of fraction of time something happened based on our experience. It connects that intuitive idea that we have of expected value or probability with the actual concept of expected value in probability or probability of an event in probability. Okay, so something interesting also to point out in those two theorems is the fact that you see that in both cases the limit is not a random variable. Okay, we define the notion of convergence in probability and convergence almost surely of a sequence of random variable to a random variable. The limit was a random variable. Here in this case, the limit is a deterministic number, which is a particular case of random variable. But you see that what's interesting is that the limit is not random, the limit is deterministic. So again, that says that if you see something often enough, then the empirical mean, or the fraction of time this happens, is going to converge not to something random, but something deterministic. All right. So, so how do we prove those theorems? Like I mentioned before, we are going to prove the theorem assuming that the common variance of all those random variables is equal to a sigma square, which is finite. It turns out that those two theorems, the weak law and the strong law of large numbers, are both true even if the variance is infinite, but the proof is significantly more difficult and we need more tools to do that. In particular, we need to know about the convergence theory for martingales and apply that to reverse martingales and use something called the Kolmogorov 0,1 law. And I'm going to give you indeed a proof again of the strong law of large number without this assumption that the variance is finite, but only when we are done covering chapter 5. All right. So in this case, we just assume that, and first we are going to prove the weak law of large number. The weak law of large number is a direct consequence, is an easy consequence of Chebyshev's inequality, and then the proof is just one line, that's just this. So we apply Chebyshev's inequality. So to prove that this indeed converges in probability to mu, the goal is to look at the probability that Sn over n, the empirical mean, minus mu, okay, the absolute value of this difference, larger than epsilon, should go to 0, should converge to 0 when n goes to infinity for all fixed epsilon strictly positive. So the goal is to prove that this goes to 0 to be able to get the weak law of large number. So how can we use here Chebyshev's inequality? Well, first you see that because those xi again are identically distributed, they have the same mean. The mean is mu, and by linearity of the expected value of Sn, which is the expected value of the sum only without the 1 over n, the expected value of the sum is the sum of the expected value. That's mu plus mu plus mu n times, that's n times mu. Now, if you look at expected value of Sn over n, you get exactly this n mu, but divided by mu, again using the fact that the expected value is linear, and so you obtain that the expected value of this empirical mean is equal to mu. So that means that the mu here is indeed the expected value of this quantity. And because of that, we can indeed apply Chebyshev's inequality. Chebyshev's inequality that we just proved tells you something about the probability of that the absolute value of a random variable minus its mean is larger than epsilon. Here, mu is indeed the mean of that, so we can apply Chebyshev's inequality. And Chebyshev's inequality tells you that this probability is less than the variance of this random variable, Sn over n, divided by epsilon square. Alright, so this epsilon square is not going to do anything, it's fixed. So the goal is to prove that this variance here goes to 0. So how do we do this? That's where we have to use independence. The variance of a sum of random variables is equal to the sum of the variances plus the covariances of any possible pair of two of those random variables. In this case, because those xn are independent, the covariance of xi, xj, for I different from j, is going to be equal to 0. That's a consequence of independence. So that means that because those xn are independent, the variance of Sn, only Sn without the over n, the variance of Sn is the sum of the variances of those xi. But the variance of those xi is equal to sigma square, so eventually the variance of Sn only is equal to n times sigma square. Now, the variance is also some kind of quadratic operator, and so contrary to the expected value that is linear, the over n here is going to get out of the variance but into a 1 over n square. So eventually what we get is that the variance of Sn over n is equal to n times the variance sigma square over n square, which is sigma square over n. And that's what we get here. We get our sigma square over n divided again by this epsilon square. And of course, sigma is fixed, epsilon is fixed also, so this thing does not move, but the 1 over n, obviously, when n goes to infinity, this 1 over n goes to 0. That's how we prove the weak law of large number. So something interesting in the proof is the fact that if you look at a random variable, then this random variable may have a variance that is kind of big. But if you look at many of those random variables, at least assuming that they are independent, if you look at many of those random variables and you divide by the number of them, so basically you look at Sn over n, then eventually you reduce the randomness of what you obtain, and so the variance of this Sn over n is considerably less than the variance of only one of those. Okay, so that's kind of the spirit behind the law of large number. If you look at enough of those realization or outcomes of a random variable and you look at the empirical mean of them, you are going to reduce the randomness and eventually converge to something that is deterministic. In this case, mu. Okay, so that's the proof of the weak law of large number. So how can we now prove the strong law of large number? Well, you see that to get the strong law of large number from this probability here, I'm going back basically to the proof of the fact that convergence almost surely implies convergence in probability that we did before. Instead of looking at only this event, we kind of need to look at the lim sup of those events. Okay, so so that we have in fact convergence almost surely. What we want is that those events occur for only a finite number of n. Okay, only a finite number of times this is going to happen. Okay, and this must be true for all possible choices of epsilon. Okay, so what we want to prove is that is the probability of this happening infinitely often for some epsilon strictly positive should be equal to 0. That's what we need to prove convergence almost surely. Now, the result we saw that tells us something about the lim sup of those events are the two Borel-Cantelli lemmas. And in particular, now we need to use the first one. So the first Borel-Cantelli lemma says that if the sum of those probabilities, okay, is finite, then those events are going to happen only for a finite number of n. That's what we want. The problem is that the bond we have here is not good enough. Okay, we just have that the probability of this event is of the order, is less than something of the order 1 over n. The infinite sum of 1 over n for n equals 1 to infinity is infinite. Okay, so the first Borel-Cantelli lemma does not tell us anything. The second Borel-Cantelli lemma cannot be applied either because those Sn are not independent. Okay, those Xn are independent, but Sn and Sn plus 1 are obviously not independent. All right, so yeah, we are stuck here because the infinite sum of those terms is infinite. So how can we make that finite? Well, for instance, if we replace the n by n squared, then we have an infinite sum that becomes finite. And that's the spirit behind the proof of the strong law of large number. First, we are going to prove convergence almost surely, not of Sn over n to mu, but of a subsequence. And the subsequence is going to be chosen in such a way that we take only the perfect square. So instead of looking at Sn over n, I'm going to look at Sk square over k square. We only look at those terms when n equals 1, 4, 9, 16, and so on. I'm looking at all the perfect squares. That's going to force a 1 over k square here. And then we are going to have an infinite sum that is finite. We can apply Borel-Cantelli lemma and deduce that we have the strong law of large number, not for Sn over n, but at least for a subsequence. Then, second step, we'll have to deal with what happens in between the consecutive terms of this subsequence. So first, I'm going to again apply Chebyshev's inequality exactly the same way, but instead of looking at what happens at time n or after n observations, I'm going to look at k square of n. Okay? So you do the same calculation. The probability of this event that's the same as here, that's now going to be less than the variance here of Sk square over k square divided by epsilon square. Same calculation, now you get sigma over epsilon square, but then a 1 over k square instead of a 1 over n. Now if you look at the sum of all of those, then eventually you obtain that this infinite sum here is clearly finite. That's sum over k of 1 over k square. And so that says that the infinite sum of the probabilities of those events is finite. So by the first Borel-Cantelli lemma, that does not assume anything about independence, by the first Borel-Cantelli lemma, this means that this event is going to happen only a finite number of times. Okay? For all epsilon positive fixed, that's going to happen only a finite number of times. Now, to get convergence almost surely, we don't need that only for a fixed epsilon positive small. We want that to happen only a finite number of times for all possible value of epsilon strictly positive. So that's another technical detail we need to deal with. But at least now from that, what we can say for now is that we can look at convergence of a subsequence. So I'm looking at the probability of that Sk square divided by k square does not converge to mu. The goal is to prove that this is equal to 0. Okay? We want to prove that this is equal to 0 to prove convergence of the subsequence to mu. So for that, I'm going to just say that saying that this does not converge to mu, that's exactly saying that the difference between this term and the limit, which is here, is going to be larger than epsilon infinitely often for some epsilon strictly positive. Alright? Then, if I remove this part for some epsilon strictly positive, but I just fix one epsilon, then the probability that this event here happens infinitely often, okay, that's exactly the lim sup of those events. And by the first Borel-Cantelli lemma, because the sum here is finite, and so the sum of those probabilities is finite, then we can say that without the for some epsilon positive, this has indeed probability 0, like we want. Now, the problem is that we also have to deal with the for some epsilon positive, okay? And so we have a bunch of events here that have probability 0, but we look at basically a union of all of them, okay? Now, the problem is that that's a union over all epsilon strictly positive, epsilon real number. So we have basically an uncountable union, and we cannot do much with an uncountable union. However, it's clear that if this happens infinitely often for some epsilon positive real number, then we can find an epsilon positive, but this time a rational number, by decreasing a little bit this one, but making it a rational number, so that this is indeed going to again happen infinitely often. So basically, what we can do, using some basic topology, the fact that Q is dense in R, and if something is larger than epsilon, then that should be larger than another positive number that is rational. What we can do is just say that this probability is the same as the probability of the same event. Okay, so this difference is larger than epsilon infinitely often, but not for some epsilon real number, but for some epsilon rational number, positive rational number. All right, so again, it's clear that this implies that. Okay, the fact that this also implies that, which we need to have this equation here. The fact that this implies that is again the fact that if a real number epsilon is strictly positive, then we can find a rational number that is strictly between 0 and this real number. Okay, and if this quantity is larger than epsilon for this real number, then this is also going to be larger than this other rational number that is slightly smaller. That's why we can go from here to here. I want to point out that this technique of replacing the for some real number by for some rational number is a very common technique we use in probability theory, or more generally in measure theory, to eventually turn uncountable union into countable union. And we have to use somewhere that Q is the topological closure of Q is equal to R to be able to do that. All right, so now, because we only look at the positive, strictly positive rational number, now we have probability that of this event, so this larger than epsilon infinitely often, that's the lim sup, okay, of those events. And we look at the union of all of them, but now a countable union. And so we can put the countable union outside the probability, and that becomes a sum. Now, next step, I'm just going to use the fact that the probability of a union is less than the sum of the probabilities. Okay? So I can put the sum, like the union, like the for some epsilon positive rational number, outside the probability, that becomes a sum over all the positive rational number. Now we have indeed a sum that's countable. This set here, Q plus star, star is to say we remove 0, that's indeed countable, so we indeed have a sum. And now, last step, that's when we use the Borel-Cantelli lemma, that already explained here. I told you that by the first Borel-Cantelli lemma, because the sum of those probabilities is finite, for all fixed epsilon, this event, or the lim sup of this event, is going to occur with probability 0. So that means that this is going to happen only a finite number of times with probability 1. And so that says basically that the probability of this event, okay, this event here is exactly the lim sup of this sequence of events. By the first Borel-Cantelli lemma, the probability here is equal to 0, but now you have a countable sum of zeros that's again equal to 0. All right? And so that shows that the probability that sk square over k square does not converge to mu is equal to 0. So the probability that sk square over k square converges to mu is equal to 1. That shows indeed that not Sn over n, but at least a subsequence sk square over k square converges almost surely to mu. All right. So that's the trick we have to use to be able to apply Borel-Cantelli lemma. We need to reduce this term so that the infinite sum of those terms is finite, but then for that we have to skip and look at, for instance, all the perfect squares. Then, next step, we need to compare like the distance between this term and the closest Sn over n. So by that I mean that we are going to take a general n. Now, this n can be sandwiched between a k square and k plus 1 square. And we need to compare Sn over n and this sk square over k square. We want to prove that this quantity is very small. In the long run, it's pretty small. And so that will mean that eventually the whole sequence behaves exactly like this subsequence. And so we still have convergence almost surely to mu. All right, so for that, I'm going to do the following. You just look at a general integer n. You take after the unique integer k such that n is between k square and k plus 1 square. Then you can do the following calculation. Now, I'm looking, because I know how to control that, I'm looking at this term and I compare with Sn over n. We are interested in Sn over n, that's why I have this number here. But we know about this one, so I'm comparing both like that. Then, by using just a basic like triangle inequality, I can just inject in between some Sn over k square. Okay, so that becomes this absolute value is less than the difference between Sn over n and Sn over k square, plus the difference between Sn over k square and sk square over k square. Now we can control those two terms easily. So first, let's look at this one. Here in both cases we have Sn, Sn. So we can put the Sn absolute value of Sn outside this whole absolute value and just look at 1 over n minus 1 over k square. What is the largest possible value of 1 over n minus 1 over k square in absolute value? Well, that's switched when n is equal to k plus 1 square. And in this case, you can easily prove that the absolute value of 1 over n minus 1 over k square for n equals k plus 1 square is going to be less than 2k over k at the power 4. Okay, so this term can be bounded by the absolute value of Sn times 2k over k at the power 4. Then for the second term, I'm just saying that I'm just extracting this time the common part, so now this time that becomes k square, and I just said that this part here is just less than or equal to absolute value of Sn minus sk square divided by k square. Then, if you look at this term, you see that Sn is the sum of about k square of those random variables. Those random variables are finite mean and variance. So the sum of k of them is going to be, or the sum of n of them, sorry, is going to be of the order n. Now, n is of the order k square. So that means that this absolute value of Sn here is of the order of k square. Okay? So this number here is of the order k times k square, which is k cubed, divided by k at the power 4. That's of the order of 1 over k. Or I should say that this part is bounded by a number which is of the order of 1 over k. Same story for this part here. If you look at the difference between Sn and Sk square, worst case scenario, n is equal to k plus 1 square. The distance between k square and k plus 1 square is of the order of k, or 2k, let's say. So this is exactly the sum, absolute value of the sum of k of those random variables. Okay? They have finite mean, finite variance. So the sum of k of those random variables for k large is going to be of the order of k. So that means that this absolute value here is again of the order of k, but divided by k squared, that gives you that it's bounded by something of the order of 1 over k. So eventually, this is bounded by something of the form 1 over k. This is bounded by something that scales like 1 over k. So the sum is again something that we call a big O of 1 over k. That means that it's less than a constant divided by k. All right. So now we have that the absolute value of this minus that should go to 0 almost surely. But also, this absolute value also goes to 0 almost surely because that's of the order of 1 over k. So when k is large, this thing is very small. And so you can apply again, like use again the triangle inequality to now compare Sn over n and mu, but you inject this term in between, and then you end up with that. Conclusion, Sn over n minus mu is going to be less by the triangle inequality that I apply again, but this time I inject this term, is going to be less than Sn over n minus Sk square over k square, plus the absolute value of Sk square over k square minus mu. We know that this quantity goes to 0 almost surely. That's what we proved here. The probability that this doesn't converge to mu is equal to 0, so the probability that it converges to mu is 1, so this goes to mu almost surely. Another way to write that is to say that this goes to 0 almost surely, but then this term here, which is the same as the blue term here, is of the order, in the worst case scenario, of 1 over k, and of course, when n is large, then k also is large, and so this term here is going to be of the order of 1 over k, that also goes to 0 almost surely. Conclusion, Sn over n indeed converges to mu, not only in probability, but also almost surely, which proves the strong law of large number, at least when the variance is finite. So now let's look at a second limit theorem called the ergodic theorem, and this theorem is a slight improvement of the strong law of large number. So the first people who worked on this ergodic theorem and something that we call now ergodic theory are George Birkhoff and John van Neumann. To compare their results with the strong law of large number, I remind you here the two laws of large number, the weak law of large number with convergence in probability, strong law of large number with convergence almost surely. In this context, the assumption is that you have a sequence Xn of random variables that are independent and identically distributed. So the assumptions of the ergodic theorem are different. Instead of taking a sequence of random variables, Xn, I'm only going to take one random variable. I assume, of course, exactly like before, that this random variable is in L1, so it's integrable. The norm 1 of x is finite, so that the mean mu here is indeed well-defined and finite. All right. I'm also going to take a function f going from omega to omega and assume that this function is measurable. Instead of taking a sequence, I'm just taking a single random variable and this function, and I'm going to combine both, looking at composition of this function on the set omega to basically create a sequence a little bit like this sequence Xn, but starting with only one random variable. So we need two assumptions on this measurable function f. The first assumption is that f is measure preserving. So what this means is that for all A measurable set or event in the sigma algebra F, the probability of A should be the same as the probability of F minus 1 of A. That's what we mean by measure preserving. That means that if you look at the pre-image of any event by the function F, then you define a new event that has the same probability, and so the same measure in some sense. Notice that this quantity is well defined, okay? Because A is in F, you can indeed talk about P of A, but because also F is measurable, the pre-image of any set in F should be again in F, so that means that F minus 1 of A is indeed in F, and so you can look at the probability of this set. This set is indeed measurable, it's indeed an event. Okay? So first condition, F is measure preserving. The second condition, that's the main one, that's the fact that F is ergodic, and that's where the name ergodic theorem comes from. So F ergodic means that for any event A in F, if the pre-image of A by F is equal to A, then A should be an event with probability 0 or 1. Okay. So to understand, to kind of get some kind of intuition of the behavior of F, in this case, that's a little bit easier. Instead of looking at this implication, it's a little bit easier to look at the contraposition of that. So the contraposition of that would be, if you have any event that has a probability strictly between 0 and 1, so I want to call that an event that would be a proper subset of omega, okay? So proper subset, strictly speaking, that means a subset that is not equal to the empty set or equal to omega. Here, I want something a little bit more. I want A to be not too big so that the probability is equal to 1 and not too small so that the probability is 0. I want something in between, something that is an actual proper subset with measure strictly between 0 and 1. Okay? So if you have such an event, so some event that does not satisfy this, then that should not be true. So that means that the pre-image of A by the function F is going to be different from A. So what this means basically is that each time you take a subset which is not all omega or close to all omega or not the empty set or close to the empty set, then your function F is going to move your set A around. Okay? And so some kind of verbal description of some ergodic function like that would be to say that the transformation F stirs well the elements of omega. So that means that if you take a little omega in capital omega, and you look at f of omega, f of omega, f of f of omega, and so on, and you look at basically what we call the orbit of the element omega by the function f, then you end up with a set that's going to cover well all the set omega and not just stay in one piece of the set. That's going to go a little bit everywhere. So intuitively, with such a function, now if we look at x of omega, we fix an omega, we look at x of omega, but then after x of f of omega, x of f of omega, and so on, then we are going to look at basically a bunch of different outcomes of the same random variable x, but those outcomes are going to be all over the place on your set omega, so much that the empirical mean of those realizations, of those outcomes, is going to be again close to the actual expected value of x. And indeed, that's the conclusion of the ergodic theorem. Okay? That says that now we look at the same quantity, okay? But instead of having some xi like that, I'm looking at x, but not at the realization or at the outcome omega, but at fi omega. This f at the power I means f of I times of omega. Okay, so you look basically at an orbit of a point omega by the function f, and you look at the value of x on all those different outcomes. Again, you look at the empirical mean of that, so implicitly that defines some kind of sequence like here. So you look at the empirical mean of this, and again, that's going to converge almost surely to the expected value of x. Okay, so the conclusion is the same as here. That's again convergence almost surely of the empirical mean to the theoretical mean. Okay, now why is it an improvement of the strong law of large number? The conclusion, that's because the conclusion is the same, but it's not obvious, but in fact the assumptions are weaker. Okay, so you have a result with weaker assumptions, but same conclusion, so indeed the result is stronger for those results. So it's not obvious that those assumptions are strictly weaker than independent and identically distributed. But just to give you an example, it turns out that the ergodic theorem would apply if instead of all those assumptions, you would take an actual sequence of random variable xn that is stationary. Okay, so what we mean by stationary is the following. If you have a sequence xn of random variable, then the sequence is said to be stationary if for all n and m, the joint distribution of a block of n of those random variables, n consecutive ones, so starting from m plus 1 to m plus n, is equal to the joint distribution of x1, x2 up to xn. Alright? So you can prove that such a sequence would satisfy the assumption of the ergodic theorem. So the ergodic theorem shows that you don't need to have a sequence of independent, identically distributed random variables to have this conclusion. It's enough if you have a stationary sequence of random variables. Now, to show the connection between stationary and independent, identically distributed, just note that if you take, in this case, you know that's true for all n and m, so in particular that's true for n equals 1. If you take n equals 1, that tells you basically that xm plus 1 only is equal in distribution to x1. Okay? So by playing on the values of n and m, you can easily prove that stationary implies identically distributed. Okay? What you can also prove is that independent and identically distributed implies stationary. So how do we do this? Well, if you assume that those random variables are independent and identically distributed, then the joint distribution of this vector here of n random variables is just going to be the product of the n common distribution. But that's the same for here. Those ones have the same distribution as those ones, and they are independent. So same story, the joint distribution of this vector here would be also the product of the n common distribution. Okay? So it's clear that independent and identically distributed implies stationary. Okay? So eventually we get the following. We get that independent and identically distributed, that's the assumption of the strong law of large number, implies stationary. So a priori, that means that this assumption is stronger than the assumption stationary, but stationary also implies identically distributed, but not necessarily independent. In fact, you can prove that there exist sequences of random variables that are stationary, but not independent and identically distributed. And so what this shows is that, in fact, so what the ergodic theorem shows is that the strong law of large number still applies to sequences of random variables that are identically distributed, or a little bit stronger than that, stationary, but those random variables do not need to be independent. So that's kind of the conclusion of this slide. The ergodic theorem is a stronger result than the strong law of large number. It extends the strong law of large numbers to sequence, like stationary sequence of random variables. To conclude this video, let's look at two more limit theorems. So the first one is the popular central limit theorem, and the second one is a general result called large deviation estimates. So contrary to the ergodic theorem, none of those two theorems gives you an improvement of the strong law of large number, but they answer questions that are not covered by the strong law or the weak law of large numbers, and so they are kind of complements to the law of large numbers. Alright, so again, I remind you the two statements of the weak law and strong law of large number with convergence in probability and almost surely. In the central limit theorem and large deviation estimates, we are going to have the same assumption. We have a sequence xn of random variables that are independent and identically distributed with a finite mean mu. I'm reminding you those two statements because those two laws of large numbers are kind of the motivation behind the central limit theorem and large deviation estimates. So first, notice that by using the strong law of large number, you can easily see that Sn minus n mu over n converges almost surely to 0. So you just have to rewrite that as Sn over n minus n mu over n, that's just minus mu. And because Sn over n converges almost surely to mu, of course Sn over n minus mu is going to converge almost surely to 0. So what this tells us is that the distance between this random sum here, Sn, and n mu, and n mu is the mean of Sn, it's the expected value of Sn, this difference is going to divide it by n goes to 0, so this difference is negligible compared to n. So that says that by how much Sn fluctuates, deviates from the mean, is going to be small compared to n. That's all the law of large number says. It doesn't say by how much, like the order of magnitude of this quantity here. And so this is answered by the central limit theorem. In fact, the central limit theorem says a little bit more than that, but kind of the motivation here is we know that this is negligible compared to n, okay? But can we say a little bit more about the fluctuation of Sn around its mean, okay? It's much less than n, because we have convergence of that quantity to 0, but is it log n, is it square root of n, is it what it is exactly? So we can visualize a little bit like those fluctuations and visualize this result here in a picture. I took the particular case of sequence of random variable xn independent, uniformly distributed in the set -1 and 1. So that means that xn is equal to -1 or 1, both with probability 1/2. This trajectory here shows the sum Sn, the sum of the first n such random variables. The way you can construct that is by basically flipping a coin at each time step, and each time you get heads you go up by 1 unit, each time you get tails you go down by 1 unit. Eventually you get a trajectory like that. This is also called the symmetric random walk on the integers that we are going to study more in future videos. Alright, so that's a particular case, just to be able to visualize what's going on. So the fact that Sn minus n mu over n goes to 0 almost surely means exactly that this trajectory eventually is going to be trapped in this cone here. So the cone here, it's like the straight line with slope mu plus epsilon, and you have this other straight line with slope mu minus epsilon. In this particular case, mu, the expected value of xn, is equal to 0, okay? Because xn is equal to -1 or +1 with the same probability 1/2. Okay, that's like flipping a fair coin, so the mean is 0, and so in the picture only mu is equal to 0, but you can imagine that you have a more general mu and the cone going up or going down. All right, so again, the fact that Sn minus n mu over n goes to 0 means exactly from this picture that eventually this trajectory that keeps track of number of heads minus number of tails, if you flip a fair coin, this trajectory eventually is going to be trapped in this cone here. And so that means that even if epsilon is very small, the distance between this trajectory and the horizontal line is going to be less than epsilon n, and so that shows that eventually the fluctuation around the horizontal line, the fluctuation of this trajectory around the horizontal line are small compared to n. Now, more precisely, what we want to understand is this area here, okay? So, the mean is here, and mu is just equal to 0 everywhere, okay? And you see that, of course, at the beginning, we are close to the mean. But then Sn, due to randomness, is going to deviate from the mean by more and more and more. Okay, and so those excursions here are going to be bigger and bigger, and we want to know this length here. How does this scale exactly? That's much smaller than n, but what it is exactly. The answer is given by the central limit theorem that says the following. So let's assume also that those xi, in addition of having a finite mean, also have a finite variance, sigma square. They again have all the same variance because they are identically distributed. So they have the same variance, sigma square, which is finite. Then in this case, this quantity, Sn minus n mu, that you recognize here, okay? We knew from the strong law of large number that if you divide by n, you go to 0, so you divide by too much. The question is by how much do we need to divide so that we have a non-trivial, a non-degenerate limit? The answer is square root of n. More precisely, if instead of dividing the difference between Sn and its mean by n, if instead you divide this difference by the square root of the variance, which is the standard deviation, times square root of n, then you have convergence in distribution to the Gaussian with mean 0 and variance 1. Okay? So that says basically that if you divide by a quantity which is much larger than n, then this divided by this quantity is going to 0. But if you divide by something which is much less than square root of n, then there is a degenerate limit, basically. It doesn't converge to anything that goes all over the place. Okay? So, something interesting in this theorem is the fact that the limit, so that's limit in distribution, is always this Gaussian random variable. The density function of this one looks like a bell curve around 0. And so that kind of shows that this Gaussian random variable is kind of a universal object because it always appears as the limit in the central limit theorem, regardless of the distribution or regardless of the distribution of those xn. It doesn't matter how you choose those random variables xn, as long as they are independent, identically distributed, and of course, as long as their mean and variance are finite, then this quantity for any possible distribution is always going to converge to the same distribution. So that's something very remarkable in the central limit theorem. It's the fact that the limit is always the Gaussian random variable. So I'm not going to prove this theorem. That follows basically from a theorem called Levy's convergence theorem that was proved by Paul Levy. And Levy's convergence theorem gives you a characterization of the convergence in distribution looking at the characteristic function of the random variables. Okay? Going from Levy's convergence theorem to the central limit theorem is not really interesting. They're just a bunch of technical, like messy algebra, like technical calculus. There is nothing really deep. Levis convergence theorem is interesting, but going from Levis convergence theorem to the central limit theorem is kind of messy. It's more interesting to just focus on the result. Okay, so going back to the picture, now we can understand this better. What this means is that if you wait long enough, you take n very, very large, then those kind of fluctuation you see here by how much this trajectory is going to deviate from this horizontal line should be of the order of square root of n, okay, for n large. All right, so that's the first theorem. So now, let's look at large deviation estimates. And one of the main contributors in the field of large deviation estimates is Varadhan here. All right, so large deviation estimates answer a question that is natural if you look at the weak law of large number. But the weak law of large number is not enough to answer this question. So the weak law of large number here tells you that Sn over n converges to mu in probability, which means that for all epsilon positive, so by definition of convergence in probability, we have that for all epsilon positive, the probability that the absolute value of Sn over n minus mu is larger than epsilon should converge to 0 as n goes to infinity. That's something we can clearly, I mean, that's just rewriting the conclusion of the weak law of large number. Now, the weak law of large number says that this goes to 0, but that doesn't say how fast that goes to 0. And another natural question, like here the natural question was, this is negligible compared to n, when n is large, what is the order of magnitude? Here the natural question is, this goes to 0 when n goes to infinity. The question is, what is the rate of convergence? How fast does it go to 0? So that's the question you can answer looking at large deviation estimates. What is the rate of convergence to 0 of this probability? So again, we can go back to the picture. I again have the trajectory here. Then what the weak law of large number says is that the probability of seeing those pieces of trajectory outside the cone, the probability of those events should go to 0. So I have another picture here where I underline the trajectory when it's outside this cone here. And so the weak law of large number says that those parts of the trajectory that are not in the cone should eventually disappear, okay? But the question is, what is the probability of seeing the trajectory outside this cone, okay, for n very large? For n very large, that goes to 0, but how fast does it go to 0? That's what we are interested in now. That's at the fluctuation from the horizontal line, or the distance between this sample path to the horizontal line. That's more like those pieces of trajectories that are outside the cone. They eventually disappear. How fast do they disappear? Okay? So the answer is here. Large deviation estimates, we need to assume a little bit more, but that's a very mild assumption. In addition to independent and identically distributed, we also need to assume that this function m theta, which is equal to the expected value of exponential theta xi, is going to be finite in a neighborhood of 0. Okay? So for theta small, we need this to be bounded, basically. So that's an extra assumption we need to add there. If we don't do this, we might not have the conclusion. So this function m is called the moment generaling function. Okay? You see that xi is a random variable, but because that's inside an expected value of something, then this expected value here does not depend on I. Okay? Because all the xi have the same distribution. Regardless of xi, this quantity is always going to be the same. That depends on theta, of course, and I'm going to call that m of theta. Okay, so one basic property of the moment generating function is the fact that m of 0 is equal to 1. That's obvious. M of 0 is the expected value of e at the power 0 times xi. 0 times xi is 0. E at the power 0 is 1. Expected value of the constant 1 is just equal to 1. So you see that m of 0 is indeed finite. Now, if you can prove that it's still the case in a neighborhood of 0, okay, so this function is not going to suddenly explode in the neighborhood of 0. You have a neighborhood of 0 in which this function is still bounded. Then in this case, you can prove that there exists a gamma that obviously depends on epsilon, because you see the rate at which you go to 0 here should depend on epsilon. If epsilon is very small, you are going to go to 0 slower, but if epsilon is big, you go to 0 faster. So, but you can prove that under those assumptions, there exists a constant gamma that depends on epsilon, but for all epsilon positive, this gamma is going to be strictly positive, okay? Such that the probability that Sn over n deviates from its mean mu by more than epsilon is going to be less than e to the minus gamma n, okay? So that shows that indeed this quantity converges to 0, like we knew already from the weak law of large number. Now that's saying something much stronger, that says that this goes to 0 exponentially fast, okay? Again, even if epsilon is very, very small, your gamma is going to be smaller, but it's still going to be strictly positive. And so that shows that this probability here that goes to 0, in fact, goes to 0 exponentially fast. Okay? So going back to the picture, to conclude, this means that if you look at this trajectory, like this sample path, and you look at the pieces that go outside the cone, then the probability of seeing some excursion like that is a little bit big and goes outside the cone, the probability of seeing something like that for n large is going to happen with a probability that is less than e to the minus gamma n. That's all for today. Thank you for watching. In the next video, I'm going to cover chapter 4 of my stochastic modeling book. That's the one about stochastic processes. In particular, I'm going to give you the general definition of a stochastic process, looking also at the particular case of martingales and Markov chain. I'm also going to give you examples of stochastic processes that are or are not martingales and or Markov chains.